Previously, we talked about squares and square roots and cubes and cube roots and how they're used to calculate area and volume and other ways they're used in scientific fields and particularly electronics. Now we're going to look at how to multiply exponents together. So I'm going to stick to a base number of 2 because this will make the math easy. So 2 squared times 2 cubed is going to be equal to 2 to the power of 2 plus 3. Isn't that easy? So that's going to be equal to 2 to the power of 5, which equals 32. So I use some easy numbers to show how this works. Let's double check that. So 2 squared is equal to 4, 2 cubed is equal to 8, 4 times 8 equals what? 32. So that works. This does not work if we have different base numbers. So if I have 2 squared times 3 squared, that is not equal to 2 times 3 to the power of 2 plus 2. It doesn't work that way because the base numbers are not the same. But as long as the base numbers are the same, as I showed here, it will work, and it works anytime the base number is the same. So 6 to the 6th times 6 to the 2nd, or 6 squared, equals 6 to the power of 8. Okay, that's all I'm going to say about this because this is an electronics class, not a math class, and that's about all you're expected to know from an electronics viewpoint. We can cover this more deeply in the math class at another time. But I do want to talk about a special base number that we've already talked about briefly, but didn't explain because we just wanted to go into the fundamentals, and that is using a base of 10 to power of some exponent. We talked about this when we talked about scientific notation. Now I'm going to talk a little bit about where that scientific notation comes from. So for example, 10 to the 1, 10 to the power of 1 is equal to what? 10. What's 10 to the power of 2? That's going to be 10 times 10, that's 100. How about 10 to the power of 3? That equals 1,000. Let's put a comma there. And how about 10 to the power of 4? That equals 10,000. So there are our powers of 10, and if you recall from our scientific notation, what we're doing is taking big numbers and making them smaller. So let's see what happens if I take a number like, how about 2,347,652? Okay, well first of all what we want to do is round this so that it's not so big. So that's going to be 2, 3, it's going to be 5, 0, 0, 0, 0. So there's a good rounding for that number. Now what we want to do is take our decimal point and move it until we only have one number to the left of the decimal point. This is going to look familiar from the scientific notation because that's exactly what we're doing. 1, 2, 3, 4, 5, 6 places. So that now becomes, if we get the rest of this out of the way, that becomes 2.35, but what did we do? We divided it by 10. Each time we move this decimal point to the left one, we divided it by 10. So to express this number, we need to tell how many times we need to multiply it by 10 to get back our original number. So times 10, how many times? 1, 2, 3, 4, 5, 6. So that comes out to be 2.35 times 10 to the 6th. Let's test that out. So we take 2, 3, 5, and we want 6 places to the right of the decimal point. 1, 2, 3, 4, 5, 6. Put our commas in there, and we recreated our original number. So that's where scientific notation comes from. And as you recall, we can also do this with very small numbers. Let's do that real quickly. So let's take a number like 0.00003,524. Okay, we're going to round this again, so that's going to be 0.0000352. And now we're going to move that decimal point to the right this time. 1, 2, 3, 4, 5, 6. So we wanted to move it 6 times to put one numeral to the left of the decimal point. So now how do we express this in scientific notation? That would be 3.52, but that number is way too big. How many times do we need to divide by 10 to get to the right place? 1, 2, 3, 4, 5, 6. So that's times 10. And since we are dividing, that's a minus or negative exponent. So that tells us how many times to move that decimal point. So let's recreate that number. That's 3.52. And how many times would we move that decimal point? 6 times. 1, 2, 3, 4, 5, 6. Put it right there. 1, 2, 3, 4, 5 zeros, 6 places total. And we got back to our original 0.000005 zeros, 3, 5, 1, 2, 3, 4, 5, 3, 5. And got back to our original number. So that is how we use that particular base, and that's where the scientific notation we've talked about before comes from. So now we need to get at what we really need to get at in this lecture, and that is logarithms, because we're getting ready to talk about analog circuits, and we're going to use logarithms a lot there. So what we have is a base number to an exponent, and that equals some answer. So b to the x equals y. In logarithms, we're going to have that base number to a logarithm, I'll just put a log there for a logarithm, equals our y. So how about having our base number 10 and our logarithm 2, and that's going to equal 100. We already did that, right? 10 to the power of 2, 10 times 10 is 100. So that means that the logarithm of the base of 10, so there's our 10, and there's our logarithm. So the logarithm of the base of 10 of the number 100 equals 2. So that might be a little confusing right now. Normally, when we're using the common logarithm, which is log to the base of 10, we just leave that out. So let's rewrite that. So the logarithm of 100 equals 2. So the base 10 logarithm, the base 10 logarithm of 100 equals 2. Well, we're not going to dive into it any deeper, but I needed to expose you to this because you needed to be exposed to this. But basically, we can go back to our powers of 10 and look at what we have there. So 10 to the third equals 1,000. We've already established that. 10 times 10 times 10 equals 1,000. Therefore, the logarithm of 1,000 equals 3. Okay, so 10 to the fourth equals 10,000. Therefore, the log of 10,000, got enough zeros there, equals 4. So that's what we are looking at here. It looks a little confusing, but it's just a way of twisting around that formula and renaming things. So the log of 1,000 is 3. The log of 10,000 is 4. Let's just go ahead and write these up here, because it'll start making a little bit of sense. The log of 1,000 equals 3. The log of 10,000 equals 4. Looking familiar from our quick look at decibels. The log of 100,000 equals 5. So what do we have there? The log of 1,000 is 3. 3 zeros. The log of 10,000 is 4. 4 zeros. The log of 100,000 is 5. 1, 2, 3, 4, 5 zeros. So the base 10 log of a number tells you how many zeros there are there. And if we have a decimal point, that just tells you how many decimal places you have. So now that we've covered what logarithms are, let's see how we use them. We already looked at that in the quick look at decibels. Let's just do a quick review about that, because that uses logarithms. What are decibels? So our decibels, 3 decibels equals a 2-to-1 ratio. So decibels are always ratios. 10 decibels equals a 10-to-1 ratio. And 20 decibels equals 100-to-1. So that's where those logarithms are working in here. 30 decibels equals 1,000-to-1. So now you can see how the logarithm works into there, where once again, the log of 1,000 equals 3. And remember, decibels are 1/10 of a bell, and so that's 3 bells or 30 decibels. Okay, so we've looked at what logarithms are. I'm not going to go any deeper than that, just to show the math, because we don't need to do that kind of math. We just need to be exposed to it. And I recommend that you look at that a few times just to get it in your mind, but we're not going to actually use that very much. But we are going to use logarithms a lot, and that's because of the kind of scales we use in electronics. So let me show how this comes in handy. Let's say we want to talk about a frequency range. Let's just look at the frequency range that we can hear, which is about 20 hertz to about 20 kilohertz. I'm going to do that with zeros, just because I can. So we can hear sounds at frequencies as low as 20 hertz and as high as 20 kilohertz. Actually, we can hear more, but that's because 20 hertz is where the ear is half as sensitive to the peak, and 20 kilohertz, once again, as our ear becomes less and less sensitive, it reaches the halfway point at 20 kilohertz, which of course is, what's the halfway point? The halfway point, which is a 2 to 1. What's that? What's that? 3 decibels. So that's where that comes into play. When we hit that half power point, which is the 3 decibel loss, that's considered the limit on either end of the scale. Now let's try to draw that scale. I'm going to draw it. Okay, let's put 0 hertz right here. Give us plenty of room. And let's put 20 hertz right here. And I'll just say this is hertz along here. Now let's put 100 hertz about here. Does that look about right? Yeah, 100 hertz. Now let's, well, where are we going to put 1,000 hertz? We can put 100 hertz, 2, 3, 4, 500 hertz about there, and we've run out of room. I just don't have the room to get all the way up to 20,000 hertz, so I need a lot more room than I have here. So we're going to have to shrink this scale. So let's start at 20 kilohertz, way over here, right about there, and let's put, let's put about the halfway point about there. So that's going to be 20 kilohertz. That's going to be about 10 kilohertz. And where's 1 kilohertz? 1 kilohertz is about here. And where is 500 hertz? It's about here. Where's 100 hertz? About there. How about 50? Oh, that's getting to be a problem. How about 20? Things are getting bunched up down at the other end. So if we make our scale wide enough that we can see what's going on at the low end, the high end goes off the board. If we try to make it so we can see what's going on at the high end, the low end, everything gets all squished together. So what can we do? Well, let's use a scale like this. First of all, let's not have a 0. Let's just have a 10. Okay, what we're going to do is double that, or actually going to multiply that by 10 to 100. Then we're going to multiply that by 10 again. Are we going to go all the way over? No, what we're going to do is double the distance when we multiply by 10. So we're going to double the distance. So let's just kind of estimate it about from there to there. Let's right about there. Don't need to be perfect. 1,000 hertz. Now I'm going to move that over just a little bit. I'm a little shy of, I think that's a little better. 1,000. Now if we go about the same distance to here, 10,000, and then right about here is what? 100,000. So if we simply double the distance every time we go a power of 10, we get these equal spaces on there. And I have things spaced fairly evenly. So look what happens when I look at the spacing. Let's see, 20 kilohertz is going to be right about here. So there's our limit of our hearing range. That should be 1,000 right there. Got that corrected. And so what we have down here, 10 to 20 is going to be, the 20 hertz is going to be right about there. We got 100, 500, where's 500? 500 is going to be maybe right about there, 500 hertz. And then 5,000 hertz is going to be maybe right about there. So as we get lower in the scale, things get stretched apart. kind of convenient. As we go higher in the scale, things get pushed together, and that gives us something that looks kind of even. Well, it looks kind of sloppy now, so let's just make a nice, easy version of the scale to where we're going to have, there's our 20 hertz. Let's put 100 right about here. Let's see, that would put 10 right about there. Just need to get a scale here, right about to there for 1,000. Oops, that should be 100. There we go. 1,000 hertz right about here. Then I need to make that about the same distance for 10,000. And then 100,000 is going to be around here. That's going to put 20,000 right about there. So there's our whole scale stretched out. Now, the nice thing about a logarithmic scale is, one, so how easy I drew that? Equal space, equal space, equal space. Every time we multiply 10, that's an equal space. Now, let's see, where's 200 hertz? It's right about here. Notice we're multiplying by a factor of 10 from 20 hertz to 200 hertz. It's the same distance. Multiply by 10, multiply by 10. They're the same distance. Every time we multiply by 10, we're the same distance. Now let's try something a little different. Let me unclutter this. Let's double that from 20 hertz to 40 hertz. Going to be right about, probably right about there. There's 40 hertz. Now where's 80 hertz? We double that distance. We go 20 hertz to 40 hertz. So that's a 20 hertz difference. We multiply that by 2 again. That's going to put 80 hertz right about here. And so 90 hertz is going to be right about there. And the point I'm trying to make here, this is starting to look a little bit cluttered again, but if we multiply by 2, we get the same width each time. So we multiply by 10, we get the same width each time. We multiply by 2, we get the same width each time. And so it's fairly easy to draw a logarithmic scale for a quick purpose like this by knowing that particular aspect of them. Multiply by 10, equal widths. So if I want to draw a real quick logarithmic scale, I can just draw 2 lines and say that's 1 and that's 10. And now where's 100? Same distance. Where's 1,000? Same distance. Where's 10,000? Same distance. Now where's 2? That's a little tricky. It's somewhere, it's not going to be even because these numbers are getting closer together, but I can give an estimate. I'm going to say 2 is right about there. Let's see how close I got. If everything works right, I should be able to squeeze this in here. If that's right, then 4 should be right about there. And then 2, 4, double it again. That should put us at about 8. Look at that. Look at that. Not quite perfect, but there's 2, 4, and 8. And where's 16? We double that again. It's going to put 16 right about there. Now this is probably more confusing than useful at the time, but just notice that if we multiply by 10, it's the same distance. Multiply by 2, it's the same distance. But if we look at a typical logarithmic scale, we're going to see something that looks like this. So let's just draw one cycle here. So let's make that a 1 and that a 10. And let's draw a 9 there. Let's see how close I can get. A little bit wider is an 8, 7, 6, 5, 4, 3, and 2. So notice I'm getting further and further apart. How well did I do? So here's 2 and 4 and 8. Close enough for a quick drawing. But notice how they get 9, 8, 7, 6, 5, 4, 3, 2, 1. And if I have another cycle over here, try to get the distance right, that would be 100. I'm going to have my same thing. 9, 8, 7, 6, 5, 4, 3, 2. Now it's crude, but you get the idea. Everything gets closer and closer together. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And we're going to get that repeated for each cycle. And so that's what a logarithmic scale looks like. And if we do it both logarithmic on the vertical and horizontal scale, we get two scales that look something like this. Here's a picture of a logarithmic graph that uses a log on both scales. So that allows us to squeeze these very, very large numbers into a tiny scale. Let's take one last look at where we use this, because it becomes very useful in audio frequency ranges. So let's put 10 hertz about here, put 100 about here, put 1,000, pretty close to the middle, put 10,000 about here, and put 100,000 about there. Now notice if we put our 20,000 right about there and our 20 right about there, notice that 1,000 hertz, there's 20,000, there's 20. Notice that our 1,000 hertz is fairly close to the middle. If I drew this better, it'd be even closer to the middle. So that's why we use 1,000 hertz as our test signal for audio ranges, because it's on a logarithmic scale, it's right about the middle. Now I'm going to look at the response for an amplifier. Okay, that response at 10 hertz is almost nothing, and it climbs up, and then it kind of flattens out, maybe gets up a little, down a little, does okay, and then starts to drop down and falls off again. Now if we look at this and find out that this is a drop of a power of 2 to 1, what's that going to be? There's our peak. We drop 2 to 1, that's going to be 3 decibels. So that would be our half power point. And our half power point, I didn't quite get it perfect, but notice that it drops off and then we lose about half of our power at 20,000 hertz. Let's put our numbers here. So 20 hertz, 20 kilohertz. So we can draw the entire graph using logarithms without having to get them too close together here and too far here, or vice versa. So there's a typical logarithmic graph, 20 hertz to 20 kilohertz of the audio frequency response. If this was radio, we'd just have a different range of numbers, but we would still use a logarithmic graph to be able to fit things together. Sometimes we use a logarithmic graph on the horizontal and a linear graph on the vertical, where this would be like 10, 20, 30, 40, 50, 60, 70, depending on what we're doing, where this would be like the peak. That would be like 3 dB, 6 dB, 9 dB. So that is why we use logarithms, because we can take all these big things and squeeze them into smaller graphs. So I hope you found this useful and informative. If you did, please like it down there, give me a thumbs up, and be sure to subscribe and hit that gray bell when you do so you get notified when I put up new videos. And to help me put these videos online, you can go to patreon.com/Vocademy and pledge your support, or go to support.vocademy.net to find other ways you can pledge your support and help me make these videos and keep Vocademy free. A big thank you to my patrons and other donors. I couldn't make these videos without your help, and thanks to everyone for watching.